Welcome everybody to the summer 2025 Bayesian Statistics workshop series. I'm Quentin Reed, the statistician for ARS for the Southeast area. We have plenty of people here, so I won't make everyone go around and do introductions. And I do know most of you pretty well already from either other classes or we work together on projects. But if anybody doesn't know me, I've been a statistician at ARS for almost 4 years now. My background is in plant ecology and also kind of interdisciplinary environmental data science, and right now I work as kind of in the research support world, collaborating with ARS scientists in the Southeast on their projects, helping them analyze their data and doing all kinds of interesting data and models and visualizations and stuff like that, and also teaching classes and workshops like this one. And I'm glad that all of you are willing to participate in this, because Bayesian statistics is a passion of mine and has been ever since I was first exposed to it in grad school. You know, coming from a ecology and evolution department, that's where I did grad school at UT in Knoxville. We had a lot of real Bayesian scientists in our department, and that's sort of where I first learned about this stuff and this approach, and have been using it ever since. And you'll learn more of the details about it in a bit, but yeah, so that's one of the things that I'm really interested in promoting at ARS. And yeah, so I also forgot to mention I'm located in the Raleigh, North Carolina location, soon to be hub, and so yeah, on the campus of NC State University. So look me up anytime you're in North Carolina. Okay, so logistics. We've already had the pre-login session where most of you, I think, were there and got set up. So hopefully everything will be good there and everything will go smoothly. Unfortunately, the teaching assistant, my teaching assistant Grant, is not here today. He couldn't make it. Actually, he's in Stoneville right now. If anybody's down there, they're out collecting data there. He can't make it today, so if there are technical issues, I'll try to handle whatever I can. But hopefully we've taken care of most of that by doing that pre-session. Anyways, yes, I'm recording right now. I will post the videos and transcripts at some point, hopefully by Monday or so every week, to the Axon page, which I'll send everybody a link to. And then if you miss any part of this or want to look at the video again, it'll be there. Yes, does anyone have any questions or comments before we get started? Well, what we're going to do today, I will try to intersperse some breaks, bathroom breaks and stuff in as we go. If I forget, please let me know. And if you ever do have a question or comment during things, do not hesitate to unmute and ask or throw it in the chat. I'll try to keep tabs on I should open up the chat here so I can keep tabs on that. Okay, and mostly this is going to be hands-on. We're going to be coding together, but every day I'll give some background, a little bit of lecturing off of slides, especially today because this is many of your first introduction to Bayesian statistics and you might not know what it is at all. So that's great because I get to teach you about it, and we're gonna start with a few slides about it. So let me go ahead and share my screen here. Yes, let's share the browser. There we go. Hopefully everybody can see that. So you can see that I am on the workshop page. I'll just copy that link into the chat so that people can go to that as well if they need to. Because this is where all the information is that I'm going to be teaching off of. So if you scroll down on this page, there's all the setup instructions and everything. Here are the materials that we're going to be going off of every day. So all the lessons, there's going to be 5 lessons, 5 weeks, 5 lessons. Every lesson is in text form. So I have a full text form of every lesson and slides. And then there's worksheets, which are basically R scripts that you're going to fill in the blank as we go. If you're on the SciNet, the worksheets are already uploaded on there. So you don't need to get to them here. So yes, without further ado, let's jump into the slides. I call this a crash course in Bayesian mixed models with BRMS. I mean, 5 weeks is still kind of a crash course. I mean, it took me many semesters of repetition to really understand even the basics of what Bayesian analysis is and what it can do. So yeah, I'm still calling it crash course. It started as a 1-day thing. Now it's up to 5 days of material, but I'm still calling it crash course. And by the way, mixed models, generalized linear mixed models, even if you don't use them in a Bayesian framework, you still might use them with classical statistics. So hopefully, even if you don't get convinced of this class that Bayesian is the way to go, you'll learn something about GLMMs, which are a very powerful tool that everybody should know about. And you can apply some of that knowledge not just to Bayesian stat models, but to Bayesian and classical, what we call frequentist statistical models. Let's say what this class is here. Let me put that on full screen here. We're going to be using R and a software called STAN to fit Bayesian multi-level or mixed linear models. I'll explain how those things fit together. STAN is kind of the computational engine, and R is the interface we're going to use to work with STAN. And the R package that we're mostly going to be using is called BRMS, Bayesian Regression Models Using STAN. This is a interface that allows us to fit Bayesian models using the computational power of this software called STAN and work with them and make nice graphs, tables, predictions, and all that stuff in R. I will give you as much background and sort of theory as I think you need, but probably it's not going to be that heavy on the theory and the equations and everything. We're going to be focusing on practical skills and applications that you will use as scientists. You don't need to know every detail of how a combustion engine works to drive a car, right? But it's good to have some understanding if when things go wrong, you can know why they're going wrong or understand what things are going on behind the scenes. So we need to have some of that, but this is more about the practical applications. So yes, hopefully if you're an applied scientist in ag science, you have seen mixed models, random effects. Some people call them multi-level hierarchical models. Hopefully you've at least seen that. And we are going to be using R to actually interact with these models. Now, I'm not going to really focus that much on the R coding part of it. If you don't know R at all, you'll be able to follow along and just copy the code as we go. But it's helpful if you know some about it, especially if you've ever used the package LME4 or GLMM TMB. Those are packages that fit mixed models with classical statistics, but the BRMS package was set up to have very similar feel and syntax to those packages. So if you've used LME4, BRMS will not be that unfamiliar to you. And we're going to use tidyverse packages, including ggplot2, to work with the data and plot it, as we go. So if you've seen those before, that'll help you as well. I already mentioned this, but not only do we have the slides version of this lesson, we also have the full text version, which if you go to that page, it looks like this. So all the lessons have this full text form. So everything that I'm saying is kind of written out in prose as well. And that's useful kind of when you're following along by yourself, because not everything is on the slides. And after a while, when we start coding, we'll look at the worksheet. That's basically just an R script with some blanks missing out of it. Their dot 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 is in there in different places in the code. And the reason I'm giving it to you that way is that if I gave you just a completely blank screen to work with and you had to type out all the code, you might make a typo, get stuck, you'd fall behind. But if I just gave you all the code and you just copy paste, you don't really engage with the code and look at each part of it and what it's doing, and you don't learn. So the middle ground is to give you incomplete code and have you fill in the blanks. I think it works pretty well. And if you do still get stuck and fall behind, you can copy and paste, because I've also included a full version of the worksheet with all the blanks filled in. I recommend you not use that. I recommend you fill in the blanks yourself, but it is there in case you fall behind. You can always copy and paste. Any questions on that? Hopefully it will become more clear as we go. And ahead of time, let's think about what the objectives are that we want to learn today. Well, we're going to learn what Bayesian inference is, what the whole Bayesian approach is all about, which relies on some key concepts: prior, likelihood, and posterior. You'll hopefully learn what those are soon. And Markov chain Monte Carlo, that is kind of the computational or mathematical algorithm that we use to actually compute the answer to these models, which I'll explain. And credible interval as well. That's how we compute the uncertainty in parameters that we estimate with a Bayesian model. And those are kind of the big concepts. What are the practical skills we're going to learn? Well, you're going to learn quite a bit. We're going to write BRMS code for a mixed model, look at kind of some nuts and bolts of fitting the model, making sure it converges, it gets the right answer, and what to do if it doesn't. Read the output you get when you fit a model and understand what it means. Use different methods to compare models, see which ones fit the data better. Do Bayesian versions of hypothesis tests to get kind of like a p-value in Bayesian sense, and make plots and graphs and tables to show what we conclude from the model. All things that you'd put, in a manuscript or in a presentation. I'll focus on those practical things that you'd use in real life. Okay, that's the intro. Now on to the content. What is Bayesian inference? It kind of has a weird name. The name doesn't really tell you what it is. It just tells you who is one of the people who helped develop it, which is this person named Thomas Bayes, who lived in he was kind of a clergyman or reverend who lived in England 250 years ago. I'm not going to give you his biography, but it's kind of this approach, even though he didn't really contribute that much to it other than the very initial idea, kind of took his name on. But what is it? Well, it's a method of statistical inference, of making inferences or conclusions from data in which we use information we already know before we got the data to assign a prior probability to a hypothesis. We can use information that exists in the world outside of the data set we're trying to analyze that we already know. And then as we get information, as we add more data, we update the probability of that hypothesis. We have a belief about what the world is like, and as we get more data, we update that belief as information comes in. Now, this is not just something that's used in statistics. It's used across a lot of disciplines and fields. They used it to crack codes in World War II. It's using cryptography in more predictive fields and things like that. But we can use it. One of the things we can use it for is to estimate parameters of statistical models that we use to analyze scientific data. And that's what you all are interested in. That's what I'm interested in too. And another point I want to bring up already, and I'll keep hitting this, is that this has been around for a while, but it hasn't really caught on. It may be new to you because you didn't learn it in grad school or in undergrad or anything. And that's because in the past, it was kind of hard to do it. The software just wasn't there yet. And so people use these other methods, which really aren't as good. But now that more powerful software and also more user friendly, you no longer have to code up the Bayesian model from scratch every time, and it's open source. That's making it easier for everybody to use these techniques, and they're really starting to catch on more, which I think is a good thing. So let's delve into, I told you I wouldn't do equations, but this one is probably one of the most beautiful and fundamental equations there is. It's called Bayes' theorem, and Bayesian inference depends on it. So we're going to talk about it. And as I mentioned, it takes the name of Thomas Bayes, but really it was developed independently at the same time by a French mathematician, Laplace, who really developed it much more fully than Bayes. But it has Bayes' name. They were active at around the same time. And this famous picture, I think there's some company in England that made a neon sign of Bayes' theorem because of how cool it is and how fundamental it is to what they do. So here it is again. You can see all the P parentheses. So in probability notation, P parentheses something means the probability of something. And so what Bayes' theorem means in more English is how likely an event is to happen or something is to be true based on our prior knowledge about conditions related to that event. And so in probability notation, we read this P parentheses A pipe B as probability of A given B, or the conditional probability. That means the conditional probability that an event A will occur conditioned on the probability of another event B occurring. So if we know that B happens, how likely is A to happen? Probability of A given B. And the way we would read this equation out is the probability that A is true given that B is true is equal to the probability that B is true given that A is true, probability of B given A, times the ratio of the probability that A is true to the ratio of the probability of B is true. A little abstract. Let's give a more concrete example, and maybe it will make more sense. So let's say that A is our statistical model. It's our hypothesis about the world. We're scientists. We make a hypothesis, and then we want to know how probable is it that our hypothesis is true. And so that's first component. Right, we don't have any data yet. All we have is A, our statistical model. Probability of A would be, in this case, the prior probability that we assign to that hypothesis being true based on our subjective knowledge before we get any data. Okay, well, that's great. In our heads, we have a belief about what is true, or what we know from the literature and so forth. Let's go out and get some data, because we're scientists, empirical data to test the hypothesis. We're going to call that B. Now, if we get some data, we can then compute the probability of B given A. That's called the likelihood. It's the probability of observing the data we observed if our model A is true. And then we can use that information, the likelihood, to update our estimate of probability, to change our belief about how likely we think it is that the hypothesis is true. And that's called the posterior, probability of A given B. The posterior probability that our model A is true, given that we observed B. Before we had our prior belief of whether or not A is true, how likely it is. Now we have more information. We have a better estimate of how probable it is that it's true because we had some data. Again, this still might not make sense until we give a concrete example. But before that, I've kind of ignored, this is the posterior probability. and there's the likelihood and the prior, but what about this denominator, probability of B? Well, that's the marginal probability. It's the probability of the data. It's kind of like a normalizing constant because a probability distribution has to have an area of 1, right? Like there has to be the probability of all events added up together has to add up to 100%. So we need to basically do the math to make sure that that all works out to equal 1. And that's what that is. It just normalizes it so that both sides of the equation have integrate to 1, if that makes sense. And so if we want to restate this Bayes theorem in English, we can say, okay, so we call A the model and B is the data. So the probability of the model given the data that we observed is proportional to the probability of the data given the model times the probability of the model, which is the posterior, our belief after we get the data is equal to the prior, what we believed before, times how much the new data we got changed our beliefs about the world, right? So what we believed before is the prior times how much information that we got changes that belief, the likelihood equals what we believe now about the world. That's the posterior. And to me, that is not only makes sense from a mathematical standpoint, but practically it sort of fits with our intuition of how we go about learning as human beings. You know, you have a belief about how you think things work. If you got information that confirms that belief, it doesn't change your belief that much. But if you got new data that is not fit with what you thought before, it will change it more. That's exactly how Bayes' theorem works. Any questions so far? So let's give a very, very simple example of how this might work. So let's say you're walking down the street and there's a quarter lying there in the street, and you want to flip it and see if you get heads or tails. What would be a good prior estimate of if you flipped this coin, the probability that you would get heads? Anybody want to throw out a prior for that? 0.5. Okay, that sounds pretty good to me. Like, I mean, why would it wouldn't make sense to go one way or the other, right? Even if you thought the coin was biased somehow, there's no reason to think it would be biased in favor of heads versus tails. So 0.5 is a great prior. Well, okay, now I take the coin and I give it 10 flips and I get 8 heads. If this is you in real life, what would your posterior, you think, be for the probability of heads after you flipped it 10 times and got 8 heads? What does anyone have a answer there? So, okay, Adam says 0.8. So Adam is not a Bayesian. He is a frequentist because he only used the data that was present right there, that data set, right? He ignored everything he knows about coins and said, okay, we got 8 out of 10, so our new estimate is 0.8. But a couple of people are saying, well, their posterior is still 0.5 because um, you know, 8 out of 10 is still probable enough to occur if the true probability was 0.5, within the bounds of random noise. You could if you assumed, a binomially distributed outcome, it's still pretty likely to get 8 out of 10 if the true probability was 0.5. And because we have a very strong prior, like we think it's very likely this coin is just a regular coin that is equally likely to get heads or tails, we still have that likelihood of the probability 0.5 is high enough that we don't change our belief that much if you have a strong prior. So it's good we get different answers there. That shows the difference between the Bayesian and frequentist paradigm. Okay, new scenario. instead of finding a quarter on the street, now a shady character comes up to you out of a back alley and says, "Hey, I've got a proposition for you. Here's a quarter, okay? I'll play a game with you, and I'm gonna flip this coin, and if it comes up tails, I will pay you $1, and if it comes up heads, you will pay me $1." Okay, what would, if you decided to play this game, what would your prior estimate of the probability be? Does anyone have a prior on that one? Okay, so we still have some 0.5. So these people are very trusting and would say, okay, this guy is giving me a fair deal. Some people say, right, so not everyone's prior is the same, right? Some people say 0.5, some said 0.8, some say 0.7. Right, there's no right answer, obviously. So, and then, okay, let's say we decide to play this game. We play 10 times, and 8 times it comes up heads. We're out, we pay 8 and get 2, so we're out $6. So now maybe your prior was either, shifted away from 0.5, or it had a broader distribution. You were willing to assume that there was the chance that this wouldn't be quite a fair game. And so maybe your belief about the true probability of that coin coming up heads would change a little bit more. But the data are the same, right? Like you got 8 out of 10 both times. Well, that's why Bayesian analysis is, the conclusion we get differs not only based on what the data right in front of us tell us, but also we're allowed to use prior knowledge about the world. Yeah, so the question is the difference about intuition? Yes, to some extent. This is kind of a very simplified example, but the kind of selling point of Bayesian inference is that it allows us to formalize our intuition, to formally incorporate prior knowledge about the world into our conclusions, rather than kind of doing it in a vague, qualitative way. We can actually precisely quantify our intuition or our prior beliefs and put it in the model. And our prior beliefs isn't just some wishy-washy thing, right? It could be we did a meta-analysis of literature on the phenomenon that we're researching and found that the range of slopes that we're likely to see between height and weight of some organism is, 0.75 or something. That could be the basis of a prior distribution. It's not some wishy-washy thing. It can be very quantifiable. Yes, so you could call it, using historical information, could be incorporated into your prior. Yes, and we can keep revisiting this, and as the weeks go by, we'll talk more about it. Yes, so as I just said, in a classical frequentist analysis, you are forbidden from formally incorporating prior information of this kind into your analysis, and you would have sort of a point estimate of the probability as 0.8 in both cases, whether or not it was from the coin on the street or the shady con man coin. So the Bayesian and frequentist is what we call sort of the classical statistics, your ANOVA t-test kind of thing that you're familiar with. Those two schools of thought differ fundamentally in how they interpret probability. And Bayesian probability has a different meaning than probability in frequentist classical statistics. Probability in the Bayesian school of thought includes the uncertainty in our knowledge about an event. So let's say back before the 2016 Olympics occurred, Usain Bolt was heavily favored to win the gold medal in the men's 100-meter event, right? So if you would have wanted to bet on that or put odds on it or something, you might say, well, he's very likely to win. I would say he's the 75% probability that he will win. Well, that doesn't really have a meaning in the frequentist analysis, because the 100-meter event in the Olympics in 2016 is one single event. Either he wins or he loses. He can't 75% win. he either wins or loses. There's no probability of a single event in frequentist statistics. It's only a long run frequency that you can define probability. Like you would have to hypothetically say if the 2016 men's 100-meter final was repeated many times under identical conditions, that I think that Usain Bolt would win 75% of the time. That's how you define probability in frequentist land. But Bayesian probability can see that single event as an uncertain outcome that incorporates our imperfect knowledge about how that event will transpire. So it is a Bayesian probability is a number that best reflects the state of our knowledge about an event that can incorporate both incorporate our uncertainty about whether it will happen or not. Like if I flipped a coin and then hid it from you, yes, it's either heads or tails, but in frequentist, you couldn't say there's a 50% probability that this coin I already flipped is heads. You'd have to say, make some paraphrase of that. But in Bayesian probability, you're allowed to say, well, because I don't know, I can use my knowledge about the coin to say that there's a 50% probability that that coin that already has been flipped is heads, if that makes sense. Any other questions so far? I know this is kind of esoteric stuff, but it's very fundamental to what we're going to be talking about. Yes, so a baseball batting average, right? So it sort of depends on, I guess, Alan, the baseball batting average thing could be interpreted in Bayesian or frequentist. It just depends what population you are making an inference about, right? Like the current slump would be just like a smaller population of at bats, but versus a historical. But yes, you could use historical performance, let's say in previous time spans, as a prior on that. And yeah, so if there were 10 races prior to, these are all questions from the chat, by the way. If there were 10 races prior to the Olympics and somebody won 50%, yeah, you could, right. So that would be basically a prior on the probability of winning this event is so yeah, that's sort of like a Bayesian approach, right? You using previous data to assign a probability to an event that's about to happen. But we'll keep revisiting these questions. Yes, and it takes a while to wrap your head around it. So if you don't get it now, it's cool. Yes. Right. Maybe we would have a better idea of who was really a better runner if we repeated every event 10 times. You know, it would probably there'd be less upsets and everything, so it wouldn't be as cool. But yeah. So all that seems very simple if the statistical model in question is a very, very, very simple model, right? The statistical model of whether a coin comes up heads or tails has one parameter, the probability of it being heads or tails. It's a very simple model. Basically, in order to get this posterior distribution that we care about, we have to, like I said, integrate the denominator, the probability of the data, to make sure that the integral, the area under the curve is exactly 1, because all probability distributions have to have an area of 1, which is easy if there's one parameter or 2 or 3, but a model might have hundreds or thousands of parameters, like a mixed model where you have like a bunch of fixed effects and a random effect for a bunch of genotypes, you know, that might be hundreds or thousands. Well, to calculate that integral for that mixed model, you have to calculate an integral in hundreds or thousands of dimensions. If you ever did calculus, I mean, if you're doing it by hand, even 3 is super hard to do and, you know, takes a long time. So obviously we're going to need computers to do anything more than that. And for many years, that was just not possible with the technology of the day. Or if it was, it would be very, very slow and time consuming. So what do we do? How do we get an answer if we need to calculate an integral with thousands of dimensions? Well, there are a lot of algorithms that very smart people have come up with to quickly get a approximate answer to an integral with that many dimensions. It's not done by solving equations to get an exact answer. It's an approximation using numerical methods, which is the best you can do. And but they do very well. And these class of algorithms is called Markov chain Monte Carlo. I won't get into the details. Basically, it's a way of sampling from a probability distribution to calculate the integral by randomly sampling from that distribution. And the algorithm is called a chain because it runs in a bunch of steps, and each step depends on the one right before it. So it goes step by step. The longer you let that chain run, the closer it will get to the true distribution, the true answer to that integral. And we just let it run long enough till it's close enough for what we want. And the way you usually do it in Bayesian inference is you use more than one chain at the same time, starting at a different random starting point, and say, okay, we're going to run these chains for a preset number of samples, 1,000, 5,000, let's say. And first, they kind of randomly jump around when they're trying to find the answer, and then eventually they'll converge on the correct answer. So we usually, the first initial part of the chain, we discard that. It's called warm up. And what remains is our estimate. It's our numerical estimate of the posterior distribution. And the reason you do more than one chain is because it's a random sampling that's starting from different initial values. If you do more than one and they converge on the same answer, that confirms that we have gotten that is really the right answer that doesn't depend on the random starting point of the chains. I'll show concrete examples of this as we go. And when it comes to Monte Carlo algorithms, the best and fastest and awesomest one that I think has ever been developed is called Hamiltonian Monte Carlo. And it is implemented in software called Stan that we're going to be using. It's very efficient. It can randomly sample from an integral with thousands of dimensions and quickly converge on the correct answer in not very many steps because of the clever way that it does this sampling. Oh, and I should mention that this was, if you're interested, I put some sources for further reading about how this algorithm works. It was developed by physicists because it is based on simulating the trajectories of particles in multidimensional space, where we're actually simulating, particles move to where they follow the gradient of force. Well, in a probability distribution, you follow the gradient of likelihood of probability to the maximum, just like a particle would go to where the force is telling it to go. So that's exactly what the Hamiltonian algorithm is doing, which is pretty cool. Okay, so we're going to use Stan, but we're also going to use this R package called BRMS. What is that? It is a easy way to use Stan, because Stan, you have to write special Stan code. I'm not going to teach you how to do that. But what BRMS allows you to do is write R code, set up a mixed model that looks very similar to like a mixed model you would write in a simpler package like LME4. And then behind the scenes, it actually sets up, generates the code, and runs a Stan model using based on the arguments that you've set for it. And we'll talk about this more later, but it also has a lot of special defaults that make it work a lot quicker. It assigns reasonable prior distributions automatically for many of the parameters, and there's also a lot of mathematical tricks it uses to speed up the convergence of the Monte Carlo to get you an answer faster. So it's a great tool. I use it all the time, and hopefully you'll appreciate how good it is by the end of this workshop. I have a few more slides before we actually get into doing some coding. I'll go through these and then we'll take a break before we get into that. I wanted to also spend a little time dispelling some common misconceptions about the Bayesian approach before we get started. So let's bust a few myths. Okay, one misconception that people have is that this is a very confusing way of doing statistics. Why can't we just use the simpler frequentist method? Yes, I agree. Every time you learn a new paradigm, a new way of doing things that's different and unfamiliar to what you're used to, that is confusing. I totally get that. It was confusing for me too. Well, it's not because it's intrinsically harder to understand. It's because the frequentist, the classical methods were, and in many cases still are, the only ones that people are taught or exposed to in their schooling. So of course, this is going to seem new and unfamiliar and confusing. Well, frequentist methods, if you think about it, are just as confusing. Let's reject the null hypothesis. What is the null hypothesis? Why do we care about rejecting it? You have to imagine a hypothetical population that may or may not exist to calculate the long run frequencies of events. And so to figure out what the probability of observing an event as extreme or more than what we did if the null hypothesis were true, and so forth. That's actually not very intuitive. So it's just as confusing in a way. Another myth that I think is very damaging is that Bayes is subjective. And if you know anything about the history of statistics, R.A. Fisher, who's obviously a very smart dude who single-handedly invented frequentist statistics and everything, really did not like the Bayesian interpretation of probability. And when R.A. Fisher didn't like something, he didn't say, well, I respectfully disagree with your interpretation. He just decided to just blacklist all Bayesian approach and tell everybody it was completely wrong so they wouldn't want to do it for 75 years, which is basically what happened because people respected this guy. And really, in my opinion, this approach is no more subjective than frequentist. Like people say it's subjective because of the priors. Well, how do you know you're not just, putting your finger on the scales by putting in a prior that you just came up with subjectively? Well, all statistical approaches make assumptions and they all require prior knowledge. A prior is just one of many assumptions. And I don't think that incorporating prior knowledge is a bias that we should avoid. It's a benefit we should embrace. It can allow us to be precise and quantitative about how we incorporate that information, which is a good thing. And, if you selectively ignore prior information, to me, that is just as bad as selectively cherry picking from your data to include in the analysis. If you take a data set and throw out observations, well, you're cherry picking from the information. If you have prior information that you also ignore, that's also cherry picking information. So, I think they're both something to avoid. Another one is that, well, I can't do Bayesian because it takes too long and is very slow on the computer. Well, yeah, I mean, you've got me there. That is true. They can take a lot of computing time and memory to fit these models, although the methods keep getting better and better, so that's becoming less and less of an issue. But there's two ways around it, right? One is what we're going to be doing, coming up with better and better algorithms for Monte Carlo sampling that converge on the correct solution. And the other is there are also algorithms that give you quicker approximate solutions of the integral without having to do all that random sampling. We're kind of taking the first way. The other way, you should check out the package INLA, R-INLA. That's the other school of thought. They don't do Monte Carlo. They kind of use these approximate solutions. And yes, obviously, if you have access to a high performance computing cluster, you can do Monte Carlo sampling across a bunch of CPUs or GPUs very quickly anyway. But still, we want to be as efficient as we can. The last one is, I think, more philosophical, that, we have to either take this Bayesian approach or the frequentist approach. We can't do both. Well, to me, philosophical dogma is great, and statistical approaches should be tools in our toolbox and not dogma that we blindly follow. And in any case, the difference between Bayesian and frequentist is exaggerated. Plus, the lines are starting to blur at this point anyway. Like if you ever do model selection, if you ever did cross-validation, penalized regression, anything like lasso, anything that you do like that, that's frequentist, but it's doing exactly the same thing as priors are doing in Bayesian analysis. It's using information that's not in the data to make a conclusion. That's exactly like using a prior. So there's no reason to, you could switch back and forth and it kind of does the same thing. And especially machine learning is really blurring the boundaries there because of, the way it does that kind of regularization and cross-validation and things like that. It's very Bayesian in flavor. So, nowadays enlightened people are like, we could just use all of it. We don't have to follow one school of thought or another. And this is, to me, a very important justification for using Bayesian models is whether or not you agree with the philosophy of it, some models you cannot get the right answer with a frequentist maximum likelihood method. Like if you are doing a complicated model with a lot of random effects on a small data set, the computational algorithms in frequentist models like that R or SAS would use often like don't converge, or they fail to estimate the random effects. They just can't get the right answer no matter how hard they try. And priors can be used really not to bias things, but to just help the computational algorithms work better and get the correct answer. So for computational reasons, it can be good to use Bayes. Another one is more philosophical, and I think a problem in science that kind of contributes to the reproducibility crisis that many fields are undergoing is this black and white, yes or no, let's either accept or reject the null hypothesis if p is less than or equal, if p is less than 0.05 and that kind of thing. Well, why are we trying to say, is this effect exactly zero or not? Why does that matter? What matters is how big is that effect and what is our uncertainty of that effect size, rather than is it exactly zero? Why does zero matter? Why don't we test whether it's exactly 0.253 or anything? There's nothing special about zero. And Bayesian inference has a more direct interpretation. If we get an answer, we can say the probability of this effect being between A and B is 95%. It's just as simple as that. Versus if we ran this experiment hypothetically many times in the long run and estimated this effect that many times, it would be between A and B 95% of the time. That's like what the frequentist interpretation is. But I think in their heads, people really are thinking the simpler Bayesian interpretation, even if it's not supported in the frequentist framework. So I think it's better to just use this Bayesian approach that is more simple and direct in how you can interpret probability. Okay, that's the background. I think this is a great stopping point. I'll pause for questions and then we'll take a short break. Does anyone have any questions or comments? Okay,
Hey,
excellent.
Quentin, can you?
Yes,
Oh,
Adam,
sorry.
go for it.
Yeah, no, I was just curious. So like, it's hard to convince like a lot of like my bosses and other
Yep,
scientists I work with to kind of like,
yep,
okay, I'm going to show you this analysis and it's using this new method Bayesian. But I mean, would a good
yep.
approach to be like to show them like the frequentist approach and then also run the Bayesian and show them both that, like, is there any situation where like you couldn't tell a story if you ran it completely like a generalized linear model, but then you did another like Bayesian approach to the same data set? I mean, could have sort of weave a narrative between those two stories, or do you ever run a situation where like you get completely different results by using different methods? That's kind
Yeah,
of
so
my
like I said,
question.
it's tools in the toolbox. You use the right tool for the right job, and I think you have to make the case that this is a situation that requires it, right? We wouldn't want to like go overly fancy and alienate reviewers and things by using an overly complicated approach that is not necessary. But like I said, there are cases where the classical statistical model just simply will not work and will not get an answer. So in there, I feel like it's easy to justify the Bayesian approach. Just that's mostly what I use it for. I don't really go and look in the literature for priors and that kind of thing, which would be cool, but I mean, who has time for that, right? It's more computational. We're looking at this more from along the lines of it's a computational tool that in many cases is the only way to answer a question we care about. Yeah, to me, that's like all the justification you need most times, if that makes sense.
Okay, yeah, that does make a lot of sense. I appreciate it. Thanks, Quinn.
Yep. And we have a question about discarding the initial samples. Yes, we will talk about that definitely. I won't answer that now because hopefully it will be addressed later. So thanks for the question. So yeah, why don't we just take a break? It's like oh, on my clock 2:53, so 1:53 Central. Let's let everyone have a bathroom break and start up again at 3 Eastern, 2 Central. I'll be right. I'm going to take a break real quick, but I'll be right back and I can answer more questions or chat a little bit more. So we'll get started again in just a minute. Will we be talking on how to infer a priori relationships among huge databases when they are not known? So, Lena, are you talking about like what priors to assume if you don't have, yeah, I mean, I guess that isn't a main focus of this workshop, but that maybe is something that you and I could talk about on our own a little bit. I'll yeah, I'll talk a little bit about just kind of like priors in the sense of, well, should we be conservative and kind of put a really wide prior and say, well, we don't know if the effect is big or small, or should we be a little bit put a little tighter prior and say, well, the effect is going to be in this narrow range, and look at what effect that has on the conclusions. But that's kind of the main way I'm going to approach priors for this workshop. But anything more, because it's a big can of worms, I guess. And so anything more sophisticated than that, yeah, let's talk about that for your work, with more like dynamic models and stuff. People do use like Bayesian approach to parameterize those kind of models, which yeah, but I'm not really going to get into that. So we should talk about that on our own, I think. Okay. Yes, thanks for the question. Let's get started back again. And we are going to, at this point, from here on out today, it's going to be hands-on. So I'll share my screen again and we'll go ahead and fire up a session on RStudio server on Scinet, which hopefully everybody did all the setup steps already. I know most of you did. So we'll fire one up. Whoops, hold on. Let's see. There we go. Okay. So I will go ahead and go to the series on demand. I'm already logged in, so others of you would have to log in. Here, I'll just, if in case anybody doesn't have it, I'll copy that link into the chat. Okay, and if anybody if you fall behind and need help getting caught up, please don't feel embarrassed to ask me on the chat or just speak up. So we're going to start an interactive session of RStudio server on Scinet. So we're basically starting a job on the server that's going to let us run our code in our browser, but it's not running on our local computer. It's actually running on a giant computer in a room in Iowa. So once I'm logged in, I'm going to go to Interactive Apps and RStudio server. Okay, we're going to start this SEA stats training account, which all of you should be enabled. Series is the queue. We can ignore this QoS. We're going to use R 4.4.1 because that's the one that all the packages are installed on. 4 hours should be plenty because this thing is only going to last 2 hours from now. 4 cores because some of the Bayesian models are going to be fitting is going to use 4 Markov chains at once. So 4 cores, 1 chain per core, and a core being a processor on the server. 16 gigs is more than enough. And this should work if you type -- reservation equals Bayes 2025. that will, yeah, the hyperthreading maybe, but at least the basic way that the BRMS is set up, it requires one core per chain. There may be ways around that, but I'm not familiar with it. And then dash reservation equals Bayes 2025 will mean our job will start quicker because I've reserved a whole bunch of cores on a couple of nodes for our class, but only for today. If you ever do this on a different day that we don't have like outside of class, you want to delete this reservation because it will not work, except I've only reserved the nodes for the time slot of our class. So we'll give it a second here. There we go. So hopefully everybody can get to this point and then connect to RStudio server. Anybody need help with that? Please let me know. And now if you it may be in the Bayes 2025 project we set up last time, but if it's not, you want to go to this project drop-down menu, and if you have set up if you've opened the Bayes 2025 project before, you're going to go and click on that one there in the drop-down menu in the upper right for project, and then it'll start the session from within that project, because that's where all the packages and software are set up so that we all have exactly the same environment and all the worksheets are there too. Yeah, please stop me if I'm going too fast. Yes, can you show the RStudio server request screen again? No problem. Let's see. If I want to start an RStudio server session, I'm going to do it under the SEA Stats training account on the series queue, R 4.4.1, 4 hours, 4 cores, 16 gigs, and dash reservation equals Bayes 2025. All that should be, yes. Christian, you're all good? Okay. And Haibo, are you good too? And this is also on the, I have a screenshot of this on the workshop page too. Okay, so I'll close that. Okay, so now if you're in the project, you should have all these folders here. Yes, Alan, if you're running this locally, you will not have the project. You're going to need to get the worksheet. You're going to need to go, yes, for anyone who's doing this locally, I should have said this, go back to the workshop page and download this worksheet right here and open it inside. You'll have to just go in and open that file inside of RStudio server. This is the worksheet.
It opened automatic. It opened automatically. Opened RStudio automatically when I clicked on it, but it looked a little different. So I just wanted to be sure.
Okay.
But okay, cool.
If you have that, because we already confirmed that all your packages are installed and stuff, so you should be fine. Albeit you will have a slower time than us because I have also saved a bunch of pre-run models on the server so that we don't have to sit there and wait for the Monte Carlo to sample every time we look at a new model. But you will, unless you can actually download those pre-fitted model objects, provided that you unzip them into the proper directory, they will be recognized by Stan. I'll mention that again when we get to that point. For anyone working locally, if you want to save time, you can actually get these pre-fitted model objects, and if you save them into the working directory of your R in a subdirectory called fits, it will recognize them and you won't have to run the models yourself every time. So where you see that in this working directory, I have a directory called fits that has all the objects in it. So if you're local, you can make a directory called fits in your working directory and unzip those pre-fitted models in there, and then you won't have to, because some of them take 2 or 3 minutes to sample. So it's a bit of a time saver for the lesson. Okay, so now whether you're on SciNet, well, if you're on SciNet, you want to open this worksheet folder and then open up the BRMS Lesson 1 worksheet. So click on Worksheets and then open the first one, the Lesson 1 worksheet. And then it will pop up as a R script. So the first thing we're going to do is, now if you are not familiar with RStudio interface, I won't go into it too much, but basically the console here, down here where my cursor is where you would type in code to run line by line interactively, but you also can save code in a script, which is basically a text file that will then run code from there. Now, what I'm going to do is I'm going to highlight this block of code, which is going to load all the packages we're going to be using. It'll also set plotting options, and it will create a directory called fits if one does not exist, but one does exist, so that line won't do anything. So if I highlight line of any section of code, and I either click run or type Control Enter, either hit run or hit Control Enter, and it will run the code in the console. So I'm going to hit Control Enter. And then messages will pop up that are just, those are fine, no worries there. Some of the packages are a couple of weeks out of date, but it's no problem. You could either hit run, and also if you want to just run one line, you can just have whatever line your cursor is on. If you hit Control Enter, it will just run that one line without having to highlight. That's how we'll be running the code. Everyone good? So I'm going to go back and forth between the slides and the RStudio session. So hopefully that doesn't make anyone's eyes hurt when I switch back and forth like that. Let me close that tab there, and we'll go full screen. Okay. As I said, load the packages. That means make the functions available in our current working session that we're going to be working with today. Like I said, set the plotting theme and create the directory for the model fits. And then there's also this line of setting the BRMS options. If you remember, we made sure that CMD stan path was set when we started our session on SciNet. This will just tell BRMS to use that software for the actual model fitting. MC cores equals 4. That means we're going to use 4 cores because we all reserve 4 cores on the server. That means when we run models, we can do 4 chains at a time. And file refit on change means if we run a model that already has a saved output, it will not re-sample the entire model unless the code has changed, which is a good time saver for us right now. And I know that Alan got command stan installed, so he can run the code like this. But for people that are running it locally that were not able to install command stan, like Marina, you would want to run the line without setting the back end to CMD stan R if you're running it locally, because you don't have command stan R. Unfortunately, we weren't able to get it to work for Marina. But yes, for some reason, some images on USDA laptops have issues getting that version of stan to install, but you can still use another version of stan that's not quite as good, but it'll still work for today. So I'll go back to my server window, and I'll hit Control Enter to run this line to set the options. And now we're going to go into a little bit about the example data we're going to be using. It's a experiment that was done to look at maize yield on the Caribbean islands under different nutrient fertilization. So the joke is that we're going to use Bayes to analyze data about maize. So yes, sorry, Alan, copied what from the worksheet?
So I've got the worksheet. So I've got the 4 squares in my R square, my R studio.
Yep.
The upper left, like you've got, has what is the worksheet,
Yes.
right? And then below that is the actual console.
That's right.
So did you copy and paste from the worksheet into the console? Is that what you did?
You could, but an easier way to do it is if your cursor is on a line and you hit Control Enter or you click on Run, it will run that code in the console.
Oh,
right?
okay.
So like, yes, you could also copy and paste and hit Enter, but it's easier to you can run code from scripts line by line by either highlighting however much code you want to run and hit Control Enter, or to run a single line, you would put your cursor on that line and hit Control Enter.
Got it. Okay.
Like that. Yep.
So I would essentially hit Control Enter at line 24 and at line 28.
Correct.
Or
yes.
both. Yeah.
That's
okay.
right.
Okay.
Yep.
Got it. All right. Thank you.
You're welcome. And now we are going to read the data, import it into our R session, into a data frame from a CSV file. And I've put that St. Vincent is the name of the island where the experiment was done. So that's the name of it, stvincent.csv. On Scinet, there's a folder called data that has it in there. If you're not on Scinet, I've posted it on a URL, so you can just read it in directly from the URL. So yes, Alan and others running locally would use that line of code instead. Make sense? So yes, you can skip, if you're on Scinet, you can skip the one from a URL and just hit, although I guess it would also work, but it's quicker if you just run line 34, hit Control Enter on this line, and St. Vincent data is imported into our session. You can see it appears in the data tab up here. It's got 300 and some rows and 7 columns, and some information is printed indicating that it imported columns with certain names and everything. All good? Okay. Background on the example data set. So we're starting, this kind of gets to Adam's question of like, how do you justify using Bayesian approach to people? Well, this is kind of a simple data set. I would say classical statistical methods, mixed linear model with ANOVA and everything would work just fine and give a same answer, very similar answer to the Bayesian. We don't really need Bayesian approach for this, but we have to start somewhere and start with something simple. So this is just a very basic and easy to analyze data set from an agronomic trial. And yeah, classic, they're looking at how much maize yield changes when you fertilize it with different combinations of N, P, and K fertilizer. And it was repeated at 9 sites on one island, beautiful looking island called St. Vincent. And it is a incomplete block design. So the treatments are N, P, and K, but not every combination of every treatment is found in each block. But each of the 9 sites has 4 blocks, 4 reps, but the blocks don't all have all the treatment combinations in them. And this is a lot of the data sets I'm going to be using in this workshop come from this R package called AgriDat, which has example data sets from ag science. But I actually took one and made it a little bit, there was also multiple islands in the original data set, but I simplified and just have data from one island just to make it a little easier for starting out. Let's look at the data set. And if we take a look at the, we can look in R at the data set, and then I'll talk about what each of the columns represent. So if you go back here, you can, or let's see, what does it say in the, if you type, use the glimpse function, and so here's the first fill in the blank you have to do. What are we going to look at? We're going to look at the data set called St. Vincent. So instead of the 3 dot ellipses, you can type in St. Vincent and hit Control Enter, and it will give a brief summary of the data set. You can see there's 7 columns. There's site, which is CHR, indicating it's a character or text variable. So there's 9 different text identifiers for the 9 locations where the trial was repeated. And each site, like I said, yes, sorry. Question? Okay, cool. Each site has 4 blocks. They're labeled B1, B2, up to B4. And each block has a bunch of plots. Each plot has a unique number identifying it. And there are 3 treatments, N, P, and K, and each treatment actually has 4 levels, from 0N, 1N, 2N, 3N. So there's control where no fertilizer was added, and up to 3. Glimpse, Christian, comes from one of the tidyverse packages. It is a function in, I think, the dplyr package to give a concise summary of a data frame. And those are the treatments, and then continuous variable outcome of yield. I don't know what it is, tons per hectare or whatever it's measured in. And those are the yield numbers. Going back to the slides, we can, let me see, I think I may have this in the wrong order, but basically first thing we want to do is, yes, this might not be on the slides, but we want to convert the columns that are not continuous numerical data into a factor data type, because we don't want to, for example, treat plot as a number, because it's just an identifier. It could be called ABC, and so forth. And with the treatment variables, factor is a good data type because it is ideal for data that have discrete levels. So the way we're going to change those to factor is we're going to use the mutate function. And it says mutate across. So it means across all these columns, we're going to apply the same function to all those columns. And the function we're going to apply is factor. And, some autocomplete things pop up, but you can hit escape to make that go away. This will say, let's convert all those columns to a factor data type. So I'll hit Control Enter to run that code. And now this next section, I do not have fill in the blanks for you, because it's sort of out of the scope of this lesson to teach you how to write ggplot2 code to make plots in R. I have separate lessons for that. Let's just look at the data. Let's make some box plots to look at the distribution of yield under different treatments. And since there's like 3 interacting treatments, we're not going to think about interactions yet. We're just going to look at the main effect of each type of fertilizer. So we're going to use N on the x-axis, nitrogen treatment level, and yield on the y-axis, and make a box plot for each nitrogen level. What's the distribution of yield? Okay. So I'll hit Control Enter on here to look at that. The data set is not loading for you, Alan. Let's see. And what error do you get there? Let me see if I can get it to.
It says error in read underscore CSV parentheses HTTPS and all of that.
Yeah, this
could not find function,
Huh.
read CSV.
Okay, did you run all these library calls first? You'll need to do that.
Maybe I missed them. I thought I got them all, but
Yep.
maybe not.
If it says cannot find function, then that's going to be why.
Okay, all right, thanks.
So yeah, just highlight them all and then hit Control Enter, and it will run all of them. Okay, so here's hopefully everybody can see this, and you also should have this locally as well. You can zoom in on it too. Here's the yield by fertilization. Okay, it looks like the median yield's a bit lower if no nitrogen was added, and then it goes up as you add more nitrogen. No shocking results there. But as I said, this trial was repeated at many different sites. So let's take a look at whether this pattern, this is the overall distribution ignoring site, but now let's split it up by site. And that's what the next line of the next plotting code will add facet by site, which means we're going to make a separate panel for each of the sites. I'll hit Control Enter to run that. So here we see that there's kind of a bit of an interaction where maybe in some cases, in some sites, nitrogen is not limiting because as we add nitrogen at these sites, the yield doesn't go up. But in other sites, it's strongly limiting, and we see a very sharp trend in nitrogen yield going up as nitrogen increases, right? So it's like, well, these sites are really what's driving this overall pattern. And we can do the same for phosphorus as well, and potassium. So that's what these next plots are going to do. So I'm going to be focusing on the nitrogen at first, just to do one thing at a time when we do this analysis, but I just wanted to show you also, all I did was change x equals n to x equals p here to give you the phosphorus plot. So I'll hit Control Enter to run that. Here's phosphorus. It looks like maybe in most cases, phosphorus is not as much of a limiting nutrient at many of these sites because it doesn't have as strong of a trend, maybe a little bit in some cases. And you can also see, I forgot to mention this before, that the sites are different too. Like the baseline yield in the control group at some of these sites is lower than others, right? It's higher in some and lower in others. That's why we need to account for site in our statistical model and treat it as a random effect, because we want to make an inference about the broader population of sites on this island besides the specific ones that we did the study at. So because we want to account for that effect and treat them as a random effect. And I'll also hit Control Enter to run this line of code and see the same for potassium, for K. Once again, looks like not a huge yield benefit at most sites from adding a lot of K to the soil. So far, so good? Okay. Yes, so these are the... Now, let's talk about our mixed model fitting syntax, not in the Bayesian context yet, but in one that you may be familiar with. If you've ever fit mixed model in R, there's a package called LME4, and this is how you would set up a model. Right now, we're going to ignore treatment and only look at the random effects in the model. And the way that a model formula in R is set up is you have your dependent or response variable on the left side, and you have a tilde, the little squiggle character, separating it from all the independent variables, the predictors, the fixed and random effects. And then you have to have an argument data to say what data frame the variables come from. And so here yield is our response variable, it's our y variable, so that's what the first part of the formula, then the tilde. Then here I'm going to build this up little by little. We are not going to have any treatment effects yet. We're just going to have an intercept, a global intercept by putting a 1 in there. We're just going to say, what is the average yield across everything, ignoring treatments? And normally you wouldn't do this, but this is sort of, we're learning here, so we're building it up little by little. Random effects terms always have surrounded by parentheses and have two halves, the design side on the left and the group side on the right, separated by a pipe. The design side means what model terms will get a random effect. And here 1 means we're going to give a random intercept. And the group side is what groups will each get a random intercept. So it says 1 pipe site means each site will get its own random intercept. We're going to assume that the sort of average yield is higher at some sites and lower in others. And same with block. So since this is a block design, we also want to have a random effect for the reps, for the blocks at each site. And since there are different blocks at each site, we want to have block colon site. So block nested within site, each of those get its own random intercept as well. That's how we set up the random effects only model. Good? Well, that was how you would do it in classical statistics with the LME4 package. Well, here's our very first Bayesian mixed model. We are going to, it has the exact same model formula as you would use if you were using a frequentist model. We're fitting yield as a function of a global intercept, a random intercept for each site, and a random intercept for each block within each site. What we have to do is give the Monte Carlo sampler some extra instructions to let it do its thing. Again, we say what data it came from. Okay, we're going to do how many Markov chains are we going to have sample? Right now we're just going to do 2. How many iterations will each chain run for? We're going to do 200. How many iterations will we let be the initial warm-up? We're going to do 100. So each chain is going to run for 200 iterations. The first 100 are warm-up to try to figure out what the right answer is, and then the next 100 are going to be our samples from the posterior distribution. Init equals random means each chain will start at a random set of initial values for the parameters. And seed equals 1 will ensure that we will get the same result because it'll set the random number generator to the same state for all of us. Now, also note, I did not supply any prior distributions to this. It's going to use defaults for us. We will get into that issue more later. So this is our first Bayesian model. So let's type it all in. I've left you plenty of blanks so we can go through this little by little. So first off, it's only got an intercept. We don't have any fixed effects besides the intercept. This one is going to be 1 pipe site. Each site gets its own random intercept. Some sites have a higher average, some sites have a lower. And this one is block colon site because some blocks have a higher average and some blocks have a lower. Data equals St. Vincent because that's the data frame that these variables come from. 2 chains, 200 iterations. The first 100 of each chain is warm-up. Initial values are random, and we'll set the random number generator. And I'm going to assign this to an object called fit intercept only, because we only have the random intercepts in this model. When I hit Control Enter, it will start to sample. But first, it has to go through a step called compiling. Now, BRMS is writing Stan code, and then Stan is translating that into C++, basically, is what Stan is actually written in. So it has to compile the program. That takes a minute. Basically, compiling always takes a minute or so. The sampling of the model for this very simple model will only take about a second. But once you have more complicated models, the sampling could take minutes or hours. Yeah, so Eric and Terry, are you doing this on SciNet or on your own on your own. Okay, and did you open the Bayes 2025 project? Do you have the Bayes 2025 project open? Does it say it up there in the upper right? And your path has not been set. Okay, have other people got that as well? Some of you do and some don't. Okay, so some people did. Some people have the compiling and everything. Okay, so some people have the error and some don't. Okay, well, it's good that not everyone has that. Okay, let's see. Now, when you you probably don't see this. If you scroll all the way back up in your console, you don't see command stand path set below where the startup message for R. You do see command stand path set too. You have that in your console. That's interesting. Let's see. Can you apologies, but can you try can you please try to just go to session and restart R and see if that will help at all? Okay, so we're giving this a minute to compile. For the rest of this class.
Sorry, Quentin.
Yeah, go ahead. Yep.
Just on this issue, so you want me to just close out of this R thing and relaunch it again?
Do not close any window or anything. Just go to the session menu and restart R. Try that.
Okay.
And tell me if. Okay, so yes. By the way, for those of you, you can see that once it compiled, it took about a minute, and then it sampled in less than a second the 200 iterations. But yeah, before I keep going, let's make sure that these folks are all set. Please tell me once you restart it, and then go get back up to this point if it works. Right. Well, you're not, Christian, you have to run all the code up to that point again to load all the libraries again, because once you restart R, those will go away. Yep.
You're right. That's true. Let me do that.
Yep. So you'll have to run everything preceding. Okay. Let's see. And when you, Eric, when you restarted R, did the let's see. Well, let's try this. I will put in the chat code that you will use to manually set the stand path, because for some reason it's not detecting for you. So you're going to want to put this code in there. No worries. Let's get this right so that okay, yes, run that code, but instead of where it says XXX, put your username, like put Eric.Billman in place of those X's.
Does it matter where I insert that in the code?
You can just put it right in the console. You can put it right in the console. Okay, Terry, so the restarting worked for you. Good. Well, yeah, that's odd. Oh, I'll try to move on in a minute, but if you still get stuck, let's the next break I will try to help you, okay?
Okay. Yeah, you might have to do that because it's giving some like can't find directory.
Okay. Maybe you didn't copy things over properly or something. Let me let me in the next break we'll try to fix it, okay?
Sure.
Sorry about that. So you'll have to just like follow along without running the code for a minute. Okay, so we just sampled the model, and now we want to look at what the model summary says. And so a summary of the model output can be gotten by using the function summary and putting the name of the model as the argument. And what we're going to do before we can actually make inference and say, well, what do these models' parameters say? We have to make sure the model, the Monte Carlo algorithm, got the correct answer, the correct distribution for the parameters. And the way we do that, one way is by looking at this diagnostic statistic called R hat, which is basically the ratio of variance between the chains to variance within the chains. As the chains converge on the same correct answer, the ratio of variance between to within them approaches 1. So the closer that diagnostic statistic is to 1, the more confident we can be that our sampler has converged and is giving us the correct answer, and we can actually use the numbers it got. So let's take a look at what the statistic is for our parameters. We're going to use summary. Control Enter on that. You can see that we get a warning. Parts of the model have not converged. Some R hats are greater than 1.05. Be careful when analyzing the results. We recommend running more iterations or setting stronger priors. So you can see we get, for each parameter, we get a parameter estimate, a lower and upper interval, a standard error from the Monte Carlo, and the R hat statistic, which is, yes, at least for some of them, for like the variance due to block, it's high, which means that the chains do not have the same answer. We haven't converged. We can't really use this output. Also, there's also ESS, which is effective sample size. So if the chain has not converged on the correct answer and is just sampling the distribution, that effective sample size will be low. We want it to be as high as possible. Let me show you a more graphical way to look at the progress of the chains and whether or not they converged. But first, I want to show you also, if you use the function R hat and put a max around it, it will say what is the maximum R hat statistic across all the model parameters in this model. Let's run that line, max of R hat. So yeah, 1.09, as we saw here. If any of them are greater than 1.05, you really can't use the results of this model. In fact, I like to make all of them less than 1.01 to really get good convergence before I would use something, you know, in a manuscript or a presentation or anything like that. So yes, so this didn't converge. We can also look graphically at the chains. If we plot the model object just by using the plot function, it will show us a histogram of the distribution of each parameter and also a trace plot, which is actually showing the value of that parameter as the chain was going along sampling. And we have basically, because we had a fixed overall intercept, we have that's going to show us that parameter, the standard deviation of the block intercepts, the standard deviation of the site intercepts, and the overall error in the model, the standard deviation of the model residuals, the sigma, because we're assuming normally distributed error. So this model has a sigma, standard overall error of the residuals. We're going to see a trace plot of all those. Will the R hats be different each time, even if the parameters in the code are the same? So did you get a different result than I got? It should.
Yeah, I got 1.14.
Okay. Are you doing this on Scinet or locally?
Scinet.
Okay. Yeah, that's odd because I tried to set this so that everybody would get the exact same results. If you're using the same packages, the same versions, you know, it should all be the same random seed and so forth, should be identical. But certainly if you're running it locally, you would get a different result because the configuration of your system is going to be different. So like the random seed will not give the same result. But so it is strange if you're getting a different result. But yeah, these things are very sensitive to like system configuration and yes, the random sampling. Yeah, and possibly you ran the code slightly different than I did as well. I don't know if so yes, let's we can get in. That's sort of a bit of a side detail, so I don't want to get bogged down in that too much. Yeah, so some people got the same exact result, so at least that's somewhat reproducible. Maybe you're doing something slightly different. We could try to diagnose, but so yeah, let's plot this and take a look. Okay, so let me zoom in on this. Can you all see my zoomed version of the plot on my screen share? Okay, cool. Yeah,
it's fine. Yeah.
Yep. So basically, here's what we see. Well, we see that these distributions they look kind of uneven. And also, the thing we really want to look at in these trace plots is the yeah. So I'll just look at this one. You can see that each of the chains are kind of, sometimes they go up, sometimes they go down. They're not bouncing around one set value. Like if it converged, it would be, the chains would be moving, the value as you went through the samples would be going up and down around the value that's sort of like the mode of the distribution. But here they kind of, like in this sigma, for a while this chain goes down, then it goes up again. This one gets stuck at a low value for a while on some of these iterations. And so that is not good. That means we have not converged. We can graphically say, well, this model, the sampler has not found the correct answer yet. And the reason is mainly because I purposefully put a very, very small number of iterations and warm-up iterations that is much lower than you would use in practice, just to illustrate what a bad convergence would look like. What we want is, they say that a good trace plot should look like a hairy caterpillar. It just goes up and down. Each iteration is not correlated with the one before or after it. It just goes up and down because it's found the correct answer and is just moving randomly around it. Instead of trying to find the one with the higher likelihood, it's found it and it is going back and forth around it. Let's see what that actually looks like, so you can see an example of good trace plots. Well, the warning said, when the model is not converged, either use more iterations or set stronger priors. Well, we're not going to worry about priors yet. We're going to increase the iterations. We're going to do, instead of 100 warm-ups and 100 samplings, we're going to do 1,000 warm-ups and 1,000 samplings for 2,000 total. And we can use the update function, which should, if it works right, let you increase the samples without recompiling the model. If we use update, chains equals 2, but now iter equals 2,000 and warm-up equals 1,000 we're going to use instead. And then we're going to plot that as those trace plots and also look at the summary. We're going to use the update function. We're going to increase iterations to 2,000. And we're going to increase warm-up iterations to 1,000. I'm going to hit Control-Enter and run that. So you see this time it did not need to recompile because it's just sampling from the same model. And it did that in 1 second, at least on my side. Now let's plot that. Control-Enter. So now this is a much better look of a trace plot. You can see it looks like a hairy caterpillar, right? They're going up and down. There's not like periods where it goes up for a lot of samples and then down for a lot of samples. It just goes up and down kind of randomly from sample to sample. Not to mention the chains are mixing well. You call it mixing because the chains have reached the same point and are right on top of each other. The light blue and the dark blue are right on top of each other. So that means that the two independent Markov chains, they know nothing about each other. They started at 2 different random spots and have reached the same correct answer independently. That is a good convergence. And you can also see a much smoother histogram of the posterior distribution of the intercept and so forth. Everyone good there? And we can use the summary method to look at the parameter estimates. You can see that the R hats are all like less than 1.01 for all the parameters. And yes. And you can also, now we can actually say, okay, the model has converged. Let's actually look at the numbers it came out with. We can actually make conclusions about them. So it's like, well, the median of the posterior distribution of the overall intercept is 16. So that's like the average yield averaged over all the random variation from site to site and block to block. Sigma is 3.92. So like each individual model residual data point for each plot has a standard deviation of about 4 from this overall mean. And then there's the standard deviation due to block and standard deviation due to site. And remember, we have not accounted for any treatment effects yet, so the residual variation is still pretty high. Variation not explained by the model is pretty high because we haven't even put in our treatments yet. Let's see if we can make the residual variation a bit smaller by adding in some fixed effects later. But before we do that, let me just explain to you a little bit about what these posterior samples are. So since we took 1,000 samples, basically we have, like for example, for the intercept, there are 1,000 samples from this distribution of our posterior distribution of what we believe the intercept to be in this model. It's centered around 16, right? But then, it goes, there's a bell curve roughly, because this is assuming normally distributed error. It's roughly a bell curve between about 12 and 20, right? Because and so that is our posterior distribution of the intercept. But you can't really show a histogram all the time. People need to see numbers. So yes, we can use 16 as our estimate of the median, but how do we say what is the uncertainty around that? Yes, I forgot about this slide. Let me just go back to that. In BRMS, I've been talking about fixed and random effects, but it doesn't say fixed and random effects in the BRMS summary. It says, let's see, it doesn't say it here actually. It should say group level effects and population level effects. Maybe they've changed the output since I wrote these slides. In your BRMS documentation, though, instead of random effects, it calls it group level effects, and instead of fixed effects, it calls it population level effects. The reason for that is in a Bayesian model, everything is kind of random to some extent because we have a random distribution for all the parameters, not just the random effects. So some people say in some Bayesian literature, you will not see the term fixed effect and random effect because everything's a random variable. But to avoid confusion and to make it more consistent with other literature, you might see, I'm going to call it fixed and random still. Okay, so I mentioned, yes, we have a point estimate for the parameter, like the intercepts and so forth, but you also see 95% CI on those summaries. Well, CI doesn't stand for confidence interval anymore. It stands for credible interval. That's the Bayesian analog to a confidence interval, but it has a more direct interpretation. We can say if we have a 95% credible interval on a parameter, we are 95% sure that that parameter's value is in that interval. And if we use Monte Carlo sampling, that's based on quantiles of our posterior. Like if we had 1,000 samples from the posterior, the middle 95% of those samples, the 950 out of 1,000, the upper and lower bound of that, those quantiles are the upper and lower bound of the 95% credible interval of our parameter. We took 1,000 samples from the posterior distribution of the intercept. 95% of them were between these two values. So we're 95% sure the parameter's true value is somewhere between those numbers. Obviously, there's nothing magical about 95%, but obviously since people are familiar with using 95% intervals and see them in the literature. That's what I'm mostly going to be using in this workshop, although we'll show other ones besides 95 as well. And I wanted to show you, these are calculated automatically by the summary method, but let's say we wanted to manually calculate it because we wanted different intervals. You can pull out the parameter that you want the interval for, and then you can look at the median and different quantiles of that parameter. So how we're going to do that is this as draws df function, running it on the model. It'll take all the parameters from the model and put their posterior samples into a data frame. Then we're going to pull out one column of that data frame, the intercept, and get to the median and the quantiles. I'll show you that. We're going to use this as underscore draws underscore df. We're going to take the draws from the posterior and make it into a df or data frame. Hit Control Enter. You can see it has 2,000 observations of 55 variables. 2,000 observations because we had 2 chains that each ran for 1,000 samples. So we have 2,000 samples from the posterior distribution for each parameter. 55 variables. Why are there so many? Because all the random effects in a model are each their own parameter. Every site random intercept and every block within every site has a parameter too. And so we had 9 sites and we had like 4 blocks within each site. So that's already like 45. Then we had our intercept and the variance components as well. So all of those are parameters. So even this very simple model already has over 50 parameters. That's why our Monte Carlo is so important. We're doing an integral in 55 dimensions already for this model. And in BRMS terminology, the prefix B is put in front of all fixed effect parameters, because in statistical notation, they're called B or beta for fixed effects. So B underscore intercept is the name of the column for the fixed effect intercept. So we're going to pull out an intercept with a capital I. We're going to pull out that B underscore intercept. We're going to pull that column out. I'm going to hit Control Enter there. And I can look at the median value of that by using the median function. It's around 16.1. Just like this histogram shows. Yes, Alan, do you have a question? Oh, sorry. No. And then, yeah, go ahead. Oh, sorry. I see. Just unmuted there. Okay, and then you can look at the.
I got a strange mutation thing or mutant going on in my sound system, so I apologize.
Oh, no worries. And then the quantile. So, like, let's say we didn't want the. Yes, you might get a slightly different answer if you your code might have run slightly differently. Again, and if your random seed started from a different place, you might, right, you're getting 15.95 instead of 16.1. Well, in practice, you might want to take a lot more than 1,000 samples from the posterior per chain, because look, the credible interval is going from 12.9 to 19.1. There's a lot of uncertainty in this estimate. We have Monte Carlo sampling error. If you only do a finite number of samples, if your chain started from a different place than mine, you might get 15.9 instead of 16.1. Those are just, that is Monte Carlo sampling error. And you can get rid of it if you do lots and lots more samples. The more, if we each ran 10,000 samples instead of 1,000, our answers would converge much more closely. But again, statistical models are just estimates, right? Like statistical models are not real. They're only things we estimate off the data. So you don't want to report these things to too many significant figures anyway. I think in the literature, you often see means from statistical models reported to way more significant figures than really is supported by the data, right? Because these are just kind of rough estimates. Now, yeah, so this, if we want the 90% interval, for example, instead of the 95, we could use quantile 5 through 95. That's the middle 90%. Just to show you there's nothing magical about 90, 95, we could do it for 90 or any other, if we wanted the 99%, we would do 0.005 to 0.995, for example. So we'll do the 90%. Again, it's a little bit narrower than the 95%. It goes from 13 to 18 instead of from 12 to 20, because it's only the 90%, not the 95%. All good? Let me do one more thing, and then we'll take another quick break, and then we'll have one more hour of excitement. We should finish this lesson today. If we don't, that's okay. We can finish it next week, because this is honestly the longest and most difficult of all the lessons. In a way, it's weird because they kind of get easier as you go. This is where we're learning all this stuff for the first time. Future weeks, we're kind of starting the foundation of Bayesian today. Every week from now on, we're adding another little brick to it. So this is the hardest part. So if we have to go into next week for this one, I think it's fine. This is one I want to spend the most time on. A cool thing, like I just showed you how you can get credible intervals. Well, literally anything in a Bayesian model, any parameter or any function of the parameters has a posterior distribution. You can put a credible interval on anything. If you were in a frequentist model and you wanted to get a confidence interval on the standard deviation of random intercept, or a confidence interval on a specific random intercept, you would have to use like some workaround with the Taylor expansion, or you'd use bootstrapping or something. And it's not that easy. So it's actually, a Bayesian model makes it very easy to estimate any quantity, fixed or random, and how much uncertainty there is on it, because everything in a Bayesian model has a posterior distribution. So you can just take quantiles of any number in the model and get an interval on it, which actually is another reason to use Bayesian models, because you can more easily calculate things that you care about. Another thing you might want to do with this random effects only model is we can use variance decomposition to look at at which level the variation in our data exists. We have a function called variance underscore decomposition, and we use the reformula argument to say which random effect level do we want the variance from. We just include that part of the random effects in the formula. So if we want the variance across sites, we're going to use this random intercept by site part of the formula. And if we want the one by blocks, we're going to do the one by one pipe block within site. Block colon site means the combination of block and site. Let's look at the variance decomposition for site and for block within site. After that, we'll take a break. We're going to use here the function variance underscore decomposition. And then we're going to use the same model, the fit with more samples, underscore formula, RE meaning random effect formula. You can hit tab to automatically complete the, oops, then it makes two equal signs. And then we'll do one by site. Hit Control Enter on that. And you can see the variance ratio is 50%. So that's basically like 50% of the random variation in the data is between sites, essentially. And then we'll look at that by blocks as well. Block colon site, same otherwise syntax. Here we see that it is 0.07, the variance ratio. So that's quite a bit lower. And in fact, it even has a credible interval for it, which spans 0. So then we're saying, well, it's very important to account for the variation due to site in our model, but the reps within site are not as different from one another. Some people would use that to argue, well, we can get away with excluding the random effect of rep or block from our model because it doesn't really matter anyway, because there isn't much random variation between the blocks. I usually say not to do that. I think we should include, if our experimental design was set up with reps, we should include rep in our statistical model, even if it doesn't explain much variation, because because that's the way the statistical model should reflect the data generating process that we set up when we designed that experiment. So even if reps aren't that important, it can't hurt to keep them in the model. And that's why the Bayesian approach is good, because sometimes in classical statistics, people can't get the model to converge, so they'll simplify it by throwing out random effects. Because we have priors in the Bayesian world that make it easier for models to converge, we never have to compromise our principles and throw out random effects that we can keep the model more complex to fit our experimental design and still get the answer, which is a good selling point of the Bayesian approach. Yes. Does anyone have any questions for me so far?
I think I have one.
Go for it.
So I guess in this case, we will probably take block out, right? Or should we just keep block by sight because it explains better our design?
Yeah. So like I said, I usually recommend keeping them all in. I just wanted to show this variance decomposition to show how you can look at it. But I would, I mean, I think it's important. My school of thought is to keep the random effects in, even if they are not that far from zero, because it just can't hurt, right? Like if they're zero, then it won't really affect your conclusions anyway, so it can't hurt to include them.
Okay, got it.
Yeah. Alan?
Yeah, so essentially, because we're using the Monte Carlo method and all of these iterations, that's why not pulling the block out it doesn't really matter. We would, in a frequentist, to use your language, approach, you would pull block out because it would then give you a larger N for the second iteration of your analysis. And so by increasing your N, you're increasing the probability of getting a meaning that you want, meaningful result.
Yes.
Here, because we're using the Monte Carlo, we don't have to do that. Is that the rationale?
Well, I think that rationale could be use Bayesian or not, because yes, if we simplify the model by throwing the block random effect term out, it would, it's a term in the model that's explaining some of the variation. If we get rid of it, more variation is available to be explained by treatments. So treatment would have a bigger effect size, or it would have a more significant p-value, or if you're doing a classical statistic approach. But I mean, I'm a statistician, so I'm always going to say, well, that's not important. What's important is making sure that the statistical model reflects the experimental design as best as possible. The applied scientist wants a lower p-value and higher effect size for their treatment to get publications and stuff. So there's a bit of a conflict of interest there, right? But I don't think that's a Bayesian versus not Bayesian issue. My main point was that the Bayesian model allows us to have more, to not have to get rid of the random effects for computational reasons, because we're more likely to get converged. Eric and I have been talking about this all week. Do you have a question, Eric?
Yeah, I do. That's not related to what you're talking about now. So if you want to finish that thought, you can.
No, that was it.
Okay.
Are you still having issues with the?
No, I was able to figure out, just beating my head against a wall, somehow got it to work. But
very good.
On this last line of code with this variance decomposition, I was just wondering why, if I run it again, the numbers are very slightly different than what you're getting on your screen.
Yes. So let's see. If I run it again, will it give the same result as before? Let's take a look. Let's see. It should be, yes, it is a little bit different, because I believe that it is resampling out of the posterior distribution each time to get these estimates. Therefore, there's a bit of sampling error every time.
Gotcha.
Yeah,
I'm
and
just not used to that. I expected it
Yep.
to be identical every single time, the way
Yes,
SAS analyses
that's
are.
right. Because your frequentist analysis is not have any stochastic component to it, right? The maximum likelihood algorithm comes out with an exact answer that's like the same if you use the same algorithm every time. There's no Monte Carlo has a random sampling in it. And I think it's almost nice in a way that it changes a little every time because it kind of emphasizes that these things are not real. They're like models are not real. They're just like
Yeah.
abstractions that we use to learn about the data. Those numbers don't get too married to them, right? Because they only exist in a fake world of this computer. Like the real thing is the corn that's growing out there in an island, and we're just like trying to learn about it with a statistical model. So, but all that is to say, you should increase your number of samples a lot to where the sampling error is not influencing your conclusions, right? Like if it's changing the fourth significant figure of the answer, that doesn't matter that much, but you want to have enough samples so that Monte Carlo sampling error is not changing your inference. But we're doing low numbers here just for, efficiency of teaching. Yep.
Okay, thanks.
Yes. Let's go ahead and take another 5-minute break until 3:15 or 4:15, depending on your time zone. And I will be right back. Hey, Wei Qi, are you running that on your own computer or on Skynet?
It's on silent. So
Okay.
I'm able to do all the steps. I couldn't, it just said it couldn't find that package.
see.
It's very strange. And then I
And-
tried to install it. It couldn't install for the
And
version
you have
of the.
you are using you copied all the files over before this and everything?
Yes. So
Okay.
that's the reason I'm able to read all those in the folder. Yeah, in my.
Okay, yes. And did you yeah, you could try what we recommended before of restarting the session. Yes, and make sure that you're in that Bayes 2025 project. Since if you got that project copied over, all the packages needed for this lesson should be on there. So it's weird that that is not showing up.
The only possible explanation is to say last time when I shipped the project is I using I doing in the USDA network, so I actually
Right.
working from home today. Is it that will make an impact? But I'm still able to see that folder. I
see, but
see
yes. Let's see. So you here, let me share my screen so I can show you. 1 second.
Okay.
You should see in the upper right this Bayes 2025 project. If it says project none, then it will not work.
Okay, it's not that.
You do have that?
I have project none, so that's the reason.
Okay, yes. So if you click on this, do you have Bayes 2025 in your project list? If you click on the drop down?
No, I couldn't find.
So it doesn't say, if you click on that, it doesn't have that project showing up?
No, I don't have that. So
okay,
I probably need
but you did copy all the files over last week?
Yes.
Okay, so what you're going to need to do then is you're going to need to go and open the project. So if you, yeah, I think the easiest way to do it is go to the Files tab down here in your session, and click on this button over here. Go to Directory. This little button on the very right. You see it there?
Yeah.
And then you're going to navigate to the directory where the project is, which is /90daydata /shared / I'll put my username, but you put your username. You'd put Weiqi Luo, and then Bayes 2025 is the name of the directory.
Yeah, in there. Yeah.
Yep. And then hit enter. And once you go there, you should see this project icon, our proj. Open that. Click on it to open it.
Okay, switching. Yeah.
Yep. And so now once the session starts again, you will have all the packages will be in that environment. Everything should work.
Great. Yeah, I probably forgot the first step because you read.
No worries. No worries. And
yeah,
you can also open up this worksheets folder.
Yeah.
And if you want to cheat or whatever, you can open the worksheets filled in folder, and then here's the version with the blanks all filled in already too. So you don't have to go back in and fill in all the blanks to run everything. Yes, anybody can do that, by the way, to make sure that you're following along correctly.
Great, thanks a lot. Yeah, problem.
Sure, great. Okay, so back to the stats. We probably won't finish this lesson today, but we'll get through some more, and we've kind of covered the most important stuff. Now we're just adding a little more bells and whistles to the stat model. Well, obviously, a kind of important one is to look at the effect of treatment on yield, because it's an experiment to test that. So we've only accounted for the random variation due to site and block, but what about the fixed factors that we actually care about, the ones we experimentally manipulated by randomly assigning plots to different treatments? Well, let's pretend right now this is not a factorial experiment. Let's just think about the main effect of nitrogen for now and just look at the fixed effect of N treatment. So basically, the only thing we're going to change about our model code from last time, I'm going to call it fit underscore fixed N, a fit with a fixed effect of nitrogen. Instead of just a 1 in the fixed effect, now it says 1 plus N. An intercept and a slope, an effect for nitrogen. We're not going to do a random slope. We still have only random intercept by site and random intercept by block. We're going to assume the effect of nitrogen on yield is the same at every site. If you remember back to the data, that may not be the best assumption because some sites had an effect and some didn't. But for now, we're going to ignore that in the model. And we're just going to say, assume one single treatment effect that is assumed to be the same everywhere. Other than that, we're going to use the same. We're going to use 4 chain. By the way, from now on, I'm going to use 4 Markov chains for every model because I find it to be a good number to, the more you use, the more you can be confident that they all reach the same distribution, that is the correct answer. 4 is kind of a good working number, and we'll use the 2,000 iterations and 1,000 warm-ups. And there's this file. We're going to also, I just put 2 as the random seed. You could put any number there. This file, I've saved this model object pre-fit in the working directory, so we don't have to sit there and wait for it to compile and run. As long as you didn't change the code and put everything in right, it will just instantly load the posterior samples from a saved object on the SciNet server. If you're running this locally and you didn't download the prefit model objects, you will have to sit and wait for it to run. But the compilation takes a minute, but the sampling should not take long for this model. Again, we are not is still our response variable. Tilde to separate the dependent from independent variables. 1 plus N is our fixed effects, intercept and treatment effect. Random seed and file means we're going to load this prefit model object from file. Hit Control Enter. So you can see it didn't have to sit and compile because it just loaded from a file. If you type in the code, it's going to start sampling and stuff. Change something about the code and it detected a difference, you can hit stop to cancel that and try to fix it. Okay, so now that model, we're going to look at the summary. By the way, I'm kind of might hit this step sometimes from now on. We still want to convert. We still want to look at the arcs and plots and everything like that. Before we actually think about inference. So we'll get summary, some of our statistics as well. Control Enter on summary. You can see that our statistics.
Hi, I'm also having issues. I cannot hear him. He keeps breaking. Quentin.
Yes, can you not hear me?
Yeah, you're having a lot of sound issues, like your phone is or your computer sound system going in and out.
Okay. Sorry about that. Shoot.
Yeah, your connection is definitely delayed.
Yep.
Okay. Was it doing before? Has it been doing that all the time, or just this last minute?
Yeah, no, you're definitely lagging and freezing up now.
Okay.
In the last
well,
3 minutes, probably.
let's see. Okay. Okay. Thanks. Sometimes if I'm recording, it can use a lot of process. I could stop. Think would help. that.
Quentin is really bad. It's really bad.
Yeah. Okay, here, let me try this. Okay, I stopped the recording. Does that help at all?
No. You may have to drop out and come back into the meeting.
Yeah. Yeah. I need to do that. Let's try that. Right.
Yeah, he's frozen for me as well.
Okay, all of your movements look normal, so you're not freezing up that way anymore. Try your audio.
Yeah, can you hear me?
Yes, sir. And that's
Okay.
you got rid of the interference problem.
I see. Okay, I
lag.
didn't even know I was connected. All righty. Yes. Yes, I saw that a message came up that Teams was updating, so that could explain why why that was happening. Yep.
Quite possibly, yeah.
Hopefully. Let me just I'll just keep going with yes, I'll just mute the camera then and hopefully that will work for the rest of this time. Apologies for that, everybody. Let's see. So where were we? Okay.
You're at the fixed effect model.
Yeah, that's right. Just pulling up the screen share. Yes. So basically what we can glean from this here is if you look at it, you can see that we have now not only in the summary do we have an intercept, we also have three slopes, one for each of the, well, there's 4 levels of nitrogen, right? So there's 3 slopes. Those are the differences between the yield in the intercept level, which is 0 nitrogen. So that's like where that 13 comes from. And then we have a positive coefficient because the average yield estimated by the model is higher in the level 1, level 2, and level 3 compared to the intercept level, right? And we can let me see on the slides, we can see that the summary shows the the model converged, and our sigma, the standard error of the residuals, is smaller than what we had in the previous model because we've actually taken away some of the random variation, right? And we've explained it with the fixed effect of treatment. So not all that variation is random. More of it is explained by the model. So the error of the residuals is less than it used to be. And we have you can also see that the credible interval for the fixed effect slopes ranges between 2 and 4, for example. So we're 95% sure that the true value of that parameter is somewhere between 2 and 4. So it's well above 0. So we have evidence for an effect of nitrogen addition on positive effect of nitrogen addition on yield, right? And let me see. Actually, before I do that, let me just show you if you type plot parentheses fit underscore fixed n, you can see the trace plots for all the parameters, not just the there. Now you can see it says hit enter to see next plot. So we have more than one screen of plots. You can see here's the trace plots for the intercept as well as all the slopes. You can see that they're right, just like we saw in the summary, the 95% is somewhere between 2.5 and 4.5 there. The trace plots look like caterpillars, which is very good. If we hit return to see next plot, there's the rest of the parameters. Okay, so we'll get through a little bit more today at least. We'll at least talk about the prior distributions on the parameters, since I've kind of glossed over that so far. If we use this function prior summary, that shows what priors are used to fit the model. And those are all the defaults that were set by BRM function. We didn't specify anything beyond the defaults. So we can look at that using this function prior underscore summary. And we'll talk about what the different prior distributions are that were assumed for the different parameters. So hit Control Enter, and we'll see here are the priors. So you can see it says flat for all the B parameters for the fixed effects, for the slope, the treatment effect of each level of nitrogen. It's flat. We have made no assumption about the distribution of those parameters before we started the model. We are saying we know nothing about it. The intercept, however, BRMS by default uses a T distribution with 3 degrees of freedom, which mean is essentially the mean of the data. So this is just a computational way to get the other parameters to converge better, because usually we don't care that much about the inference on the intercept. So we can just set it to the mean of the data. And the variance, the standard deviation parameters for all the intercepts are set to a distribution with a mean of 0 and a pretty high standard deviation. And standard deviations always have to be positive. So those are basically half bell curves. They have a lower LB means a lower bound of 0. So we've basically set very uninformative priors that is not putting any prior knowledge at all really on the distributions of any of these parameters. So we're letting the data do all the work. We're not really making any assumption about any of these parameters. There is one issue though with that, especially for the fixed effect slope. So like I said, by default, they are flat priors. Flat means a completely flat uniform distribution. It assigns equal prior probability to any possible value. Meaning like the slope could be 0. It could be 100,000. It could be negative 55. It could be anything. We're saying there's equal probability of any of those values. That's not very plausible, especially because in the data, yield only ranges from 0 to like 30 or 40. So it wouldn't make any sense for the parameter to be any bigger than, 40 or negative 40, for example. So really, that flat prior is actually not very plausible. It worked fine here because the model converged, because it's a simple model, but we can actually help our model to converge if we use priors on the fixed effects that keep the values to a reasonable range. We're not biasing it by saying we think the effect is going to be big or small, or it's going to be negative or positive. We're just eliminating basically impossible values from the prior distribution, and that will help the model converge because it's not wasting time sampling impossible values, if that makes sense. Only ones that are possible. So that's kind of the most weakly informative prior we can give. We call it weakly informative because it is giving some information, but it is not giving, it's not, biasing it toward being a small effect or a big effect or anything like that. And so in this case, we want to use a good one to use would be a normal distribution with a mean of 0 and a standard deviation of 10. This is a good choice because a mean of 0 is like a bell curve centered on 0. Half of it's negative and half of it's positive. We think that positive effects are just as likely as negative. We're not biasing it. And a standard deviation of 10 is very wide. Like I said, yield only varies by like a few dozen units in this data set. So a standard deviation of 10 means we're not biasing it to the effect to be big or small. We're saying there's a pretty high probability of both small and big effects. And so we use the function prior. There's the argument prior in the BRM function, and the function prior is used to assign a prior to each class of parameters. And so if we say normal 0, 10, that's a normal with a mean of 0 and a standard deviation of 10. And class equals B means we're going to apply that prior to all the fixed effects all the slopes in the model, all the betas, the treatment effects, not the intercept, but all the treatment effects. Other than that, I'm keeping everything the same, but I'm changing the name of the object to fixed n with priors. And there I have a pre-fit model object that has that in the directory. Hey, everybody can still hear me, right? I'm afraid I'm talking to a empty room.
Yeah, no, you're good. You're good.
Okay,
You're strong.
and it's coming in good. Okay, great. Sorry about that again. Cool stuff. Okay. So all I'm doing here, like I said, this model is just the same as last time. Same model formulas. It's going to have the same likelihood, same data, but it's going to have different priors. The argument is called prior, and the function to define priors is also called prior. And it's a normal with a mean of 0, standard deviation of 10. And class equals B means we're going to put that prior on all the fixed effect slopes only. Control Enter to run that. Now, if you look from before, there's our slopes from last time, 3.4, 3.9, and 5. Let's do the model summary to look at what our estimates are now. Control Enter to run that. And they're very similar. It's 3.39, 3.9, and 4.9. So they're a tiny bit smaller maybe than last time, but not to any extent that would influence our conclusions, right? The credible interval is still between 2 and 4. It hasn't really changed much. So this prior, yes, in a way it's good, right? It means that our prior assumptions about the distribution of the parameter has not influenced our conclusions. So we don't have to really worry that our conclusion is sensitive to a prior that we've chosen. It instead, maybe in this case, it didn't matter because the model converged well even without the priors, but it can be necessary sometimes to do that to help the model converge. I'll talk for about 10 more minutes here and then mention a couple logistics, and then we'll stop because I know you can only absorb so much of this information per day, and we can always resume where we left off next week.
Hey, Quentin?
Yes.
Sorry, can you scroll up in your code chunk, or not chunk, just slightly? I missed one thing in that first chunk for the fixed and BRM thing.
Yep. Is that good?
Yeah, just give me one sec. My web browser is freezing up. There we go.
And just to let you know that you can you can get, if you go to the files and go to worksheets filled in and open this
okay,
lesson
I
one
didn't
worksheet
see.
filled in, it's all the blanks are filled in there.
Gotcha. I didn't realize
So
that
you
was,
could use that to get caught up. Yep.
yeah, I figured you had that somewhere, but didn't realize it was that
Yep.
readily available.
Yes.
All right, thanks.
Yes. I don't want to make it too obvious because I don't want people to just use that because I believe in the power of filling in blanks, but it is there in case you need it. Yes. So, and just a point I made on the slide here is that if you are reporting a Bayesian analysis in a paper or anything, you must report what priors you used. It's essential because, people cannot reproduce your results unless they know what priors you used. And, better yet, if you felt that it was necessary, you could even repeat the analysis with different priors and show a sensitivity, for example, in a supplement would be something useful to do. But that's kind of going above and beyond in a way. You don't see that too often in the lit. This is something, yeah, it's good to hit this point. Yes, Adam. Question? Do you have a question, Adam? You're muted if you're asking something. Well, I'll just keep going. Oh, I'm sorry, Lena. I missed your question in the chat about what class equals B is. That refers to the fixed effects. In the BRMS syntax, B refers to any fixed effect in the model because in statistical notation for mixed models, usually treatments and fixed effects are called beta or B. So that's why class equals B refers to the fixed effects. So that would be only the treatment slopes parameters would get that prior. Any treatment slope in the model gets the same prior if we put class equals B. Now, the next thing I'll talk about is the posterior predictive check plot. That is a very useful diagnostic. You should run this on every model that you run. It is a diagnostic for how well the model fits the data. What it's going to show us is it's going to show us a density plot, sort of like a smooth histogram of the observed data, and then it's going to show us a density plot of the predicted data from 10 random draws from the posterior distribution. It's like, how well does the model fit the data? Just like in classical statistics, you would look at the QQ plot of the residuals to make sure they're normally distributed and that kind of thing. This is kind of like that. We want to make sure this is kind of a holistic way of looking at it. Is the model reproducing the distribution of the data? Is it fitting the data well? This is a pretty basic way to look at that. If the observations line up with the real data, the observations line up with the model predictions, then that's good. So let's pp_check. Posterior predictive check is the name of the function we're going to use for that. Hit Control Enter and run that. So yes, you can see that it's kind of faint on my screen, but here the black line is the observed data, and the thin blue lines are are 10 random draws in the posterior for those parameters, and then predict out the fitted values of the model each time for each iteration, each of those 10 iterations. You can see that it's kind of generally, the posterior is generally capturing the data, but there's kind of these two peaks. I believe that, well, we've kind of left out some model terms. For example, we've left out the phosphorus and potassium fertilization treatments, and we've left out random slopes for site. So maybe, generally it's capturing the shape of it. We don't have like a highly skewed thing or anything, but maybe if we added more model terms, we could get a better fit to the data. Because we've kind of intentionally left out treatment effects here because I'm trying to build this up little by little for you. if we look at that summary method, right, we got the median and the 95% credible interval for the parameters. Well, there's nothing special, like I said, about 95%. We can work with the full posterior distribution. And that's what I use when I make tables and graphs of results from a Bayesian model. I'd like to report more than one credible interval, not just 95. 95 is kind of a relic of null hypothesis significance testing, where p equals 0.05 is the cutoff, right? Like if you're using 0.05 as the cutoff, a 95% interval is sort of the same decision rule. If a 95% interval includes 0 or not, that's similar to saying if p is less than or equal to 0.05. But there's nothing special about 0.05, so it's better to show more than one type of interval. And there's a package called Tidy Bayes, which has a bunch of methods that work with BRMS models that help you pull out samples of parameters and make tables and graphs out of them. And one of those functions is called gather draws, and it can pull out posterior samples of parameters that we choose from a model that we can then work with. So we want to gather draws from this model fit object. We want to get the parameters for the intercept and the 3 treatment slopes for nitrogen. And remember, they all begin with B because they are fixed effects. B intercept, B, N1, N. So that means B, the name of the factor is N and the level is called 1N. So this is the slope for the 1N level of nitrogen treatment, and then N2N and N3N. So we want to gather draws. I'll go through this this section here up to line 134, and then we'll stop for the day, and we can finish next week. B underscore N1N, B underscore N2N, and B underscore N3N. And we can run that line of code there. And if we use the function called median underscore QI, that means get the median and the quantile credible interval for all those parameters. And so that will do it for, we can do it for any interval we want. So I like to do 66 and 95 because if you have a normal distribution, roughly 1 standard deviation is about 66% of a normal distribution is within 1 standard deviation, and 95% is within 2 standard deviations as a good rule of thumb. So you can use those. Those are usually good ones to report. And then I just threw 99 in there as well. So we can do that median underscore QI. And you can see, so yeah, here's the median and then the lower and upper bound of the different intervals. You can see the 66 interval is a lot is narrower because it's only 66% of the distribution is within it, and then like the 99% interval is wider. 99% of the of the samples are within that interval. Okay. And you want to do estimated marginal means, right? Like people don't necessarily want to know the difference between the control group and each level. They want to know what the estimated mean is like for each level, like not just the difference. It's harder sometimes to interpret the difference in yield between level 1 and the control. We just want to know what is the yield in the control, what is the yield in the treatment group, right? So we can do that by just adding the slopes onto the intercept for each of the 3 levels, and that's an estimated marginal mean. And we can do that for each draw from the posterior distribution. And so you can use a package called EM means to do that automatically, but I want to just show how it's done sort of by hand before we would go to that. So all we need to do, like for example, if we wanted to get the mean for the level 1 treatment, we would just add the intercept, that's the mean of the 0 treatment, and then add the slope for 1, which is the difference between 0 treatment and 1 treatment. And that would give us the mean for the 1 treatment. And then we can get the mean and 95% interval or any interval we want for that quantity. So let's do that. We want to add, first we have to reshape the data to get them into columns, right? So we normally don't do this because I normally just use the EM means package to get these means, which some people call least square means, but I'm just showing you how you would do it longhand first. So the B underscore intercept is the name of the parameter, the intercept parameter. And then we'll add on, that's the mean of the 0 group. And then we'll add on the difference between 0 and 1, and that'll give us the mean for the 1 group. We'll run that line of code, and then we can get the median and interval for that. So, right, because the intercept is about 13, and the 1 group has a mean about 3.3 higher than that. So this one will be about 16 when we add those two up. So there's the mean is about 16, and we're 95% sure that the value is somewhere between 13 and 19. Okay. I think that, here, let me see if I can put the camera on again, and hopefully it doesn't get mad at me. So yes, I think it took us a while to get started today with people getting technically on the same page and so forth, but I think now we're running more smoothly as long as Teams doesn't get mad at me in the future. Hopefully everything will go good, and we can keep this thing moving. So I think next week I will spend a little bit of time finishing up with this lesson, because this is sort of the most fundamental one, and then we'll continue on from there. And I do want to point out, if you let me, before we go, I'll go back to this page. You can see that if you go to the text version of the lesson, the full text version, and scroll down to the bottom, or there's exercises. I've made little homework problems for you if you really want to work on this stuff. I've included some homework problems, and I have an answer key for that as well. So if you're interested in going further with this stuff, you can do those. So yeah, does anyone have any questions before I wrap up? I appreciate folks sticking around. So what I'm going to do now is, you can go ahead and save this worksheet, and that'll save the blanks you filled in so far. And then I'm going to go ahead and close this browser window.
Sorry, Quinn.
Yes,
can you hear me now? Sorry, I've been
yes.
trying for like 5 minutes to get my mic to work.
Oh, shoot.
This is probably a stupid question, but I just had a really quick question. I'm kind of going back to the regression coefficient estimates for the intercept, and then the N1N, N2N, and N3N.
Yep.
So when I'm building generalized linear models with trapping data with mosquitoes, a lot of the times, like, we're looking at like getting less mosquitoes in for a repellent we're testing, right? But occasionally the repellent ends up becoming an attractant, and we get more than compared to the control.
Yep.
So do these regression coefficient estimates, they follow the same, like if it's negative, it's a reduction compared to the control, and if it's positive, so it's the same, basically the same thing.
That's right. Just in this case, as it so happens, the intercept control group has a lower mean than all the treatments, so every single slope is positive.
Sorry.
Okay.
I can. I didn't dare hit ringing for a moment because I was in the Bayesian statistics class.
Yep. So yeah, that's oh, someone has error object B N1N not found. And what sorry, Anju, where is the error coming up? You're trying to run like this line here?
Yes. The one I'm running.
Okay, and Did you run everything before that?
Yeah, I did.
Let's see. You did this, you typed, yeah, I mean, as long as you type everything exactly like this, it should work. If your posterior slopes.
I have my back. I didn't put this on the and one that one there. Thank you.
Oh yeah, so yeah, Eric, I'm about to just talk about that. Yeah, just in terms of logistics to wrap up. I believe that if you, I don't really use this RStudio server on Signet that much. I'm pretty sure if you close this out and quit the job and start again, it should restore the session to where it was last time. But if it doesn't, we will just rerun the code together. So I'm pretty sure we'll find out next week whether the yes, okay, so yes, you do have to, yes, it might not be able to preserve that session state. You could save it, but I think the best thing to do is just to rerun it next week. As long as the prefit model objects were saved, then the code should work. It should be very quick to rerun. So that's probably the best thing to do. We'll just do that next week. So yeah, so I'm just going to close this out. And then you can cancel the running job if you want. It can't hurt to cancel it. And then yes, that's right. It's probably, oh yeah, maybe I should do that. Well, I'll just connect back to this. If you, yes, you probably you could save the workspace and then do that. Yep. But if you do this way, it will end the session, and then you can, I believe I've set mine to not save the state, but some people get prompted to do so. Next time I'll just rerun everything. So I'm going to quit this job and cancel it. And now next week we'll start over again. So yes, that was your first introduction to Bayes, and hopefully it was not too harsh of one. And we will resume next week, finishing up some of the basics on mixed models, and then we'll do a little bit of generalized linear models, which is lesson 2 in the series. So yes, again, thank you all so much for participating. Sorry for the technical difficulties. Hopefully it will not be an issue next week. Yeah, I've done this a lot of times and haven't had that before. So hopefully it's a one-off. Thanks again. Thanks again for participating, and I'll stay on for a minute in case anyone has any questions. Otherwise, I'll see you next time.
Hey, thanks, Dr. Thanks, Dr. Reed. We appreciate you doing this. It's pretty outstanding.
Very good. Glad you liked it.
Hey, Quinton.
Yes, Alex, how are you doing?
Good. How are you?
All right.
Good. That's my first time. Thank you very much. I followed, well.
Good.
So I will, read and practice, in the coming weeks. But I have one question for you. If I want to use Signet for, R.
Yep.
Should I request space for it, or I don't know how to? Yeah.
Yes. So you need to like the project you're on now is only for training. So you have to request a project allocation. There's a form on the website to do that. And basically, if you get that, it gives you like a directory with 1 terabyte of space on it. And then when you like start, you know how we selected the account at the drop down and it said SEA stats training, you would have, if you create a project, you would have other accounts, and then you have to select an account to run a job. And so then it will log like how much but it doesn't cost money to your research unit or anything. You just have to, it's just like for accounting, you have to do that. Yep.
Yeah. So once I get the space, and then it's just, I can access for R Studio server, yeah?
You could, yes, and you can use other applications as well. We're just
Okay.
using the RStudio server now. You can use other ones. You have to upload any data you want to work with. You have to upload
Okay.
using the this application called Globus. You have to install that on your computer to upload data to SciNet.
Okay.
There's a lot of tutorials online about how to do it.
Okay.
So, and then you can, you should follow those.
All right. I'll try. Thank you, Quinton.
Yeah, my
Appreciate
pleasure.
it. Yeah, right.
My pleasure.
Yeah.
Anyone else still have any questions or not? Looks like not. All right, I will close the recording.